My name is Joe Kassar, and I'm the Application Engineering Manager for Rapid Controls Prototyping and other left-hand side of the V-Cycle products at dSPACE. Today, I'm here to present to you what Rapid Controls Prototyping solutions dSPACE has available for the university market and other markets for the development of control systems using model-based design. So I guess a lot of, we should start off explaining a little bit about what exactly we mean by rapid controls development and prototyping. Basically, the idea and concept here is that you can take a controls engineer can take a concept, a control idea that they want to implement in a real application, a real vehicle, or maybe in the laboratory. Something that requires deterministic real-time controls, such as an electric drive system or a internal combustion engine controller, really any type of actuator control that is deterministic and requires safety controls to be implemented for performance. And so what a system like this should provide is quick design capability, which means that you need the ability to take a model, something created, for instance, in Simulink, in MATLAB Simulink, and basically get it to the point where it can be loaded onto a piece of hardware. And that hardware is what dSPACE provides. And so what is really important is that this process eliminates the need of any sort of programming by the end user. So the expectation here is that the end user is a controls domain expert that basically has some experience using classical controls theory, and he wants to implement it. He may not have the ability to code. So this is why these type of systems are useful and valuable. Comprehensive support of I/O and network interfaces in a vehicle, for instance, are another requirement. Being highly scalable so that you don't run out of processing power, and the different type of diverse I/O, also very important. For in-vehicle applications, the system has to be robust and reliable, and the system should be basically able, because they're expensive, it should be that the system has long-term support. That's not something that you invest in and you expect to be able to use for many, many years. And so here's an example of one of our prototype systems that's been used in an application. This is at Audi, and basically this is a pilot driver that for an autonomous type application. The role of the MicroAuto Box here was basically to control the driving actuators, the throttle, steering, and braking systems. And so it provided a platform for the controls guys to design their algorithms to take sensor fusion data from the other perception computers in the system you see there, and to realize the effect on the braking, throttle, and the steering based on that perception. And so they chose this platform because it was easy to program with MATLAB Simulink, very easy to get integrated. Obviously, these type of applications have the the timeline is very rapid, and they need to be able to get these prototypes out fast, and then to change software very quickly. And so that's a good example of using a system in a vehicle. So here's the process. The process is you start out with MATLAB Simulink. Here you might just be running on a computer like a laptop. You do your design offline, meaning you don't have any real hardware involved. You get the controller working the best you can in the simulation environment, and once you do that, it's time to take it to the real system. And so we offer a variety of products for that, which I'll go over later. But the idea here is that it's basically a control system with a high-end microprocessor and maybe some FPGAs. And it's basically that we have the tooling that lets you target our hardware with the Simulink diagram. Once you're running, then you basically integrate with whatever actuators you want to basically realize closed loop control. And it can replace, for instance, a production controller that is in a vehicle or in whatever manufacturing environment, whatever environment you're in, this system would replace it. Can also kind of coexist with it. And this is what we have with coexisting. So if you already have interface electronics that you want to keep in the loop, then it's simple also to just add on a real-time system to take care of the parts that the factory system isn't capable of doing. And of course, the factory controller can interact with our systems using the various network technology that's available, like Ethernet, CAN bus, and others, for just some examples. So on-target bypassing is a third concept, and here you actually don't even need hardware. We can take your environment and your Simulink model and then load it onto the factory controller. In this case, there are some requirements for the factory controller, like it has to have available free RAM space and enough hard disk space also to be able to facilitate loading onto the rapid controls prototyping application in memory while maintaining its current course. So this is an interesting concept, and it is worth mentioning. However, if you really do need additional horsepower, then it's not a solution. So how do we get your Simulink model to run on a real system, on our system in a real environment? And the first question you're probably asking is that you need to be able to actually have access to the I/O that is part of the system. And for that, we have a variety of blocks that we provide to let you instrument your model to bring in the interfaces to the external world into your Simulink world. And so here you can see, for instance, analog inputs, digital inputs, digital outputs, vehicle buses, all the stuff you see in these palettes here. There's an FPGA. It's very easy to instrument, just dragging and dropping. And this is a conventional way we provided dSPACE systems in the past. It is changing a little bit into the future, and then here's the next slide is our future, and it's actually really our current interface called configuration desk. So now instead of actually instrumenting your model, what we're having you do is basically import your Simulink model into a tool called configuration desk, and then the I/O interfacing is done there. Now, one of the big advantages of that is that your Simulink can remain completely neutral on space environment. So that when you want to use them later on, for instance, for production coding and passing them on to other users, you don't really need to worry about the dSPACE instrumentation. It's all done here through configuration desk. We also have a tool called the Bus Manager that lets you import vehicle networks like CAN, DVC, and ARXML onto the system. And then so in either case, whether you use RTI or configuration desk, the result is the same. You get an executable that can be flashed onto your dSPACE system that will run your control algorithms that you've written in Simulink. After you've got an application running on the controller, whatever the dSPACE controller is that you're using or your factory ECU, the next stage would be testing. So now you have to actually get into your vehicle or on your dynamometer to test, for instance, if you're doing electric drive control, you'd want to be able to test that. So you need a human machine interface, you need HMI and a user interface for that. We provide control desk for that, which is completely integrated. Basically, what you do is you import a variable description, which is automatically generated for you from the build environment. That lets you map out the variables that you want to trace, plot, and also to tune. So data acquisition, as well as parameter tuning or calibration, as we call it, to be able to calibrate the gains and constants in your model to get the desired performance throughout your testing. Control desk offers a large range of instruments to use for that. So we have plotter arrays, XY plots. You can load even visual, like graphics, to better illustrate what you're doing. There's all sorts of, obviously numeric inputs and slider bars, rotary switches, anything that you might want. In addition to that, you can also basically do CAN logging and other type of logging directly in the tool itself. So this is sort of like your main user interface. Okay, so another concept here is model-based design with a field programmable gate array. A field programmable gate array is actually a logic device that's capable of running very fast. So it's a little bit different than what we call a processor CPU, which is what we normally use for prototyping. This is more of a hardware device, and it requires a special tooling block set to be able to use. And the manufacturer of the FPGA, this particular FPGA that we use, is called Xilinx, and that company provides a tool called the system generator that lets you design in Simulink using their block library diagrams that would run on their FPGA. And we have also then provided tooling to support this use case. Here's an example of one example of the use of this system generator tool, and it's to do electric drive control, where a very fast current control loop has to be executed. It's so fast that it wouldn't execute on a normal CPU, and therefore we use the XSG to basically provide that, to do that controls. And here you can see it's a DQ transform that's used to basically control current and PWMs to the motor, to the three-phase windings of a motor, to generate the current through the motor. And so you can partition basically the slow part to run on the CPU, which is done in traditional Simulink blocks, and then basically there's an interface that lets the FPGA take care of the more high-speed complex current controller. All of the space platforms that we have available will support this FPGA use case. So these are the three that I'm going to talk about today, and I'm going to get to in the next couple slides: the MicroAuto Box, the MicroLab Box, and the Scalexio modular system. All three provide the ability to do FPGA-based rapid prototyping. The first that I'll talk about is the MicroLab Box. The MicroLab Box is basically a compact lab system. It's very powerful. It has a dual-core 2 GHz PowerPC 5020 as the main processing element. It has a large Kintex 7 FPGA, for instance, for handling all of the I/O, and also available for prototyping at the FPGA level. So you can do what I had described in the previous slide. It's competitively priced for university customers through our ACE kit. So this is a great starter system. It has a lot of I/O, over 100 channels, about 100 channels. As you can see, analog inputs, analog outputs, digital I/O, PWMs, 2 CAN buses, and 2 Ethernet ports. Oops. Okay, so the next platform is the MicroAuto Box. Now this is more of a compact system that is meant for in-vehicle use. It is actually a quad-core 1.4 GHz ARM as the main processing element. You can basically get a MicroAuto Box that has the FPGA option. Also, it would be a dual-layer MicroAuto Box, so it would be a little different than what you're seeing here, which is a single layer, but the idea is the same. You get basically a similar type of performance, maybe not as powerful as some other systems, but definitely a lot of power. It has the ability to do data logging via USB, so you don't need to have a computer with control desk attached if you just want to put this in a vehicle and drive it around and then collect data and then upload it later. So that's one key difference, I think, from the other system. As well, it has a lot of bus support, because what we see in vehicles, like the autonomous example that I showed earlier, there was a significant need for vehicle network interfacing. And so that's why we have a lot of capability for CAN, LIN, and Ethernet. The final system that I'll talk about is the Scalexio modular laboratory and in-vehicle system. So the concept here is that now, instead of having these like single units that are not expandable, we have this modular concept. So what you do is you pick a chassis, whether it be a laboratory chassis or an in-vehicle chassis, which is what you see towards the right in the presentation, and then you pick I/O cards. So, and as well as a processor card. So what you're seeing there is the processor card for the system. It's called the DS6001, and basically it's an Intel i7, quad core running at 2.8 gigahertz, And then I can pick a variety of I/O cards based on my example. So if I need analog inputs or digital inputs and I need very scalable, very scalable or unique requirements, this is a unique system. The same cards will also go in the in-vehicle chassis. The in-vehicle chassis is called the MicroAuto Box, and it's what you see at the bottom. This system architecture provides a full complement of any sensor actuator interface cards that you might need for embedded controls. It offers a multi-core as well as multi-processor system configuration, meaning that I can design an integrated system from various Simulink models and then basically have them interface together and communicative over a deterministic fiber optic network that is proprietary to dSPACE. So we ensure that the system is lockstep when it executes across multiple processor boards and cores. That is the end of my presentation, and thank you very much for your attention here. And obviously, if you have any questions regarding this presentation, please get in touch with us. We have, I'm sure that the information for the contacts will be provided at the end of this recording. Thank you very much.
dSPACE, your partner in simulation and validation.